Hi. So in this lecture we want to talk about time complexity and space complexity. So in general we can say we want to talk about complexity analysis. So what does it mean when we say complexity analysis, or specifically time complexity slash space complexity? So what are these terms? See, so the basic funda behind these terms is what we want to do is we want to understand, given an algorithm A, so we have a problem P. We thought of an algorithm A for as a solution to this problem. Now we want to figure out how good or bad this solution is, right? So given a problem, you can have many algorithms, but you would want to figure out how good or bad a particular algorithm is. So we would want to do that for multiple reasons. First of all, before we implement it, or before we go ahead and decide that this is the algorithm which is good enough for us, we need to know how much time it's going to take, or how much memory it's going to require. Secondly, if you have multiple algorithms, what do you want to do? In case you have multiple algorithms, you would want to figure out which one to use. You have multiple solutions, you would want to pick the one which is fast, which doesn't require a lot of memory. So, in order for us to make these decisions correctly, we would need to know how much time and space each algorithm requires. So in this lecture, we want to focus on finding these numbers quantitatively, not just qualitatively. I don't want to say seems like algorithm A is going to be faster than algorithm B. That's not good enough. I want to know how much faster. Is it 10 times faster? Is it 100 times faster? What exactly is the scale at which one algorithm is better than the other one? So we want to quantitatively figure out how good or bad an algorithm is in terms of time as well as in terms of the memory requirement, or you can say space, right? So that's what we want to achieve in this lecture. So given an algorithm A, what we would want to do is, in a way we want to reach this function. It's not going to just depend upon the algorithm, it's going to depend upon the input size as well. So we want to get to this function which is time taken by algorithm A for an input size of n. That's where we want to get to. How much time will an algorithm A take if I give it input size n? Because obviously if the input size increases, the time taken is going to increase. Whatever be the algorithm, if I ask you to sort 10 numbers and if I ask you to sort 1000 numbers, the amount of time you require is obviously going to be different. So we want to get to this function which tells us how much time an algorithm A is going to take for an input size n. Similarly, we want to find the space requirement of algorithm A with respect to input n. That's where we want to reach. And it's very important that we reach here because that's the only way we will be able to figure out which algorithm is better, how good or bad a particular algorithm is, and that's going to help us make the right decisions. Whenever somebody asks you to solve a data structures problem or an algorithmic problem, in all likelihood, as soon as you give a solution, their next question is going to be, hey, what is the time complexity of your solution? What is the space complexity of your solution? That's where this lecture is going to be very, very helpful in figuring out these numbers so that we just like finding a solution is not good enough. You need to know how good or bad that particular solution is. Okay, so that's what we're going to do in this lecture. From the next session onwards, we will be looking at like there are a couple of ways of doing all this analysis. We will look at both those ways, and hopefully by the end we will be able to find the time complexity and space complexity for all the algorithms that we have seen so far, right? You will have to do that as an assignment. We will solve time complexity and space complexity for multiple problems in this lecture, and then you will need to go back and look at all your assignments and try to find the time and space complexity of whatever code you have written so far. Okay, thank you. Hi. So in this session, I want to look at one of the methods of finding these time complexities as we talked about in the previous session. See, so for now, let's just focus on time complexity, and whatever we will discuss, very similar things can be done to find the space complexity as well. Okay, so for now, whatever we're going to talk about, we're going to talk about time complexity. Okay, so to find this time complexity, one thing we can do is we can experimentally find this function. We call it experimental analysis. The idea is very simple. I have an algorithm A, let's say A1. Let's write code for A1. Once I have code for A1, I will give it an input size of, let's say, 10 and see how much time it takes. Then I'll give it an input size of 100 and I'll see how much time it takes. Then I'll give it an input size of, let's say, 1000, and then again I'll see how much time it takes. So that ways I can plot a graph that how much time an algorithm is taking with respect to n. And by looking at the graph, we will get some sense of the function that we were looking for, the function that we wanted to get to. What was that function? Time taken by algorithm A for an input size n. So if I have the graph, using that I can look at it, or generally I can get a sense, okay, so it's if n goes 10 times, my time taken also increases by 10 times. That means it's more or less linear to the input size, right? So whereas if I increase it by 10 times and my time increases by 100 times, and again I increase it by 10 times and it again increases by 100 times, then it kind of telling me that a tenfold increase in n means 100-fold increase in time taken. That kind of mean that we are looking at an n square kind of an algorithm, something that runs square of the input size, right? So that will give us some sense around how much time our algorithm is taking. Okay, so that's what we want to do in this session. So in this session, what we will do is, instead of looking at just one algorithm, we will look at two algorithms. We'll pick A1 and A2. A1 will be merge sort, right? Merge sort, and A2 will be selection sort. Both of these algorithms are supposed to sort given a list. If you give them a list, they are supposed to sort that list in increasing order. So what we are going to do is we're going to test them for different values of n and see how much time each algorithm takes, and if we can make some sense of which algorithm is better, how much time each is taking. Like, we will try to see whatever we can interpret by looking at the running time of these algorithms as respect to these values of n. Okay, so what I need to do is I need to implement merge sort, I need to implement selection sort. Both these things I hope you know already how to do it. So I have already written code for it. One thing that I would need an array or list of size n, and I'm going to take it to be in decreasing order. So my data will be this way. Okay, so I need to so like I could pick any kind of an array, but I don't want to pick something which is like this, which is already sorted, right? Then sorting this array doesn't require a lot of effort in case of some algorithms. So just to be safe, I'm just taking it to be reversed order, and the algorithm is supposed to sort it into increasing order. So that's what we are going to focus on this session. Okay, so let's look at some code. So I have already written code for merge sort, I already have code for selection sort, and I have also written a function which returns a reversed array given n. Right, pretty straightforward. So there are better ways of creating an array which is reversed. You can do it in single line, but for now let's not focus on that. Let's just worry about like how to calculate the time taken by each of these algorithms. So let me run these codes. Okay, so we have these. Now what do we need to do? We need to take, let's say n is equals to 10. We need to create our reverse array, and now let's just focus on merge sort for now. So let me call merge sort on A, and seems like, okay, sorry, it requires n. Yeah, so merge sort should have sorted the array. It has sorted the array for us, right? Uh, just in case you want to see this as well, originally the array was reversed, but merge sort sorted into an increasing array. Okay, so let me remove this. Now what we need to do is we need to figure out how much time it took. So how can you do that? So I think we should, if I had a timer, I'll start the timer here and I'll stop the timer right after merge sort call. Stop timer. And I'll look at the difference in time that will tell me how much time merge sort took. So that's pretty straightforward. In order to do that, we can import, there is a library in Python, we can import that, it's called time, and it can help you measure time. So for example, there is a function called time within this time library which gives you the current time with a lot of precision, right? So these are seconds and this is like 6 more levels of precision that this particular function is giving you, right? So right now it was at 40 and it seems like I explained this thing in 20 seconds, so now it is at 59, right? So we can use the time command from this time library. How will we do it? We can do it this way. Start is equals to time dot time, end is equals to time dot time. I'm not going to print A. Let's assume A got sorted, right? We are calling merge sort. Merge sort we have already learned. I've written the code which I've tested thoroughly. So let's not worry about whether A is sorted or not. Let's print end minus start. This will tell you the time taken by merge sort. So seems like it took 0.0001 second. Extremely fast for n is equals to 10. And n is equal to 10 is a very small number, so not surprising. Let's just print, while we are printing n minus start, let's print n as well. So if I give two arguments, it prints both of them with a space in between them. So it's telling me 10 and then 6.6, 10 to the power minus 5. So this time seems like it took this much time. So even less than previous. It's actually interesting because I have run exactly the same algorithm on exactly the same array. I created the array again. So this time the array was not sorted. It's not that this time array was already sorted. I have created the array again on purpose. Now the array I created again was in reversed order. So previous time when I gave this same array to merge sort, it took this much time. But this time again when I ran it, it took a little lesser time. Why is that? So that's because this is not the only program running on my computer. There are a bunch of other things that are happening on computer, right? So whether how much time your algorithm is going to take is not just dependent upon the algorithm, it depends upon the environment as well. So to do the experimental analysis properly, ideally we should do it on a machine which is dedicatedly doing only this work, right? Which is dedicatedly doing only this work. That would give you the correct analysis. For now, there will be changes, there will be differences between how much time each run of an algorithm is going to take, and let's just bear with that, right? It's not going to be major, it's not going to be that one time it is taking 20 seconds, the next time it's taking 200 seconds, it will be like sometimes it is taking 20, sometimes it will be taking 22, 18, so like it will be within that range, but it will not be exactly same amount of time every time, okay? Cool. So now let me create another cell and this time let's copy this code and let's call selection sort. And just to point out something again, I am creating this array again because merge sort has already sorted this array. I don't want to give that sorted array to selection sort. So I'm calling this function again so that every time I call selection sort, I'm sure that the array was reversed order, right? Okay, perfect. So let's run this again. Okay, and let's run this. Seems like they are both very fast. This one is taking this much time and your selection sort has taken this much time. Not much of a difference. Previously we ran merge sort was taking almost this time, that like almost the same amount of time as selection sort. So at such small input you can't really compare. So let's not worry about something for this small an input. For now, if you want to write it down here, let's write it down. So merge sort is taking 6 and this is taking this much time. Now let's try for 100. Okay, for 100 again it's very fast, not much of a difference. Sorry, to increase the font again, just 1 second. Yes, okay, so how much time did it take? 0.0003. so here it took 0.0003 and this one took 0.0005, right? Am I correct? Yes, that's how much time it took. Now let's try 1000. Okay, so it is increasing, and a little more significant difference between the two, right? This is almost 10 times of merge sort. Selection sort is almost 10 times of merge sort. So 0.008 and 0.09, 0.008 and 0.09. Still these numbers are so small that I will not rely on them, right? We need to try bigger numbers. Okay, and selection sort is still running. It's taking a lot more time than previous run. This time it has taken 6 seconds. Merge sort is very quick. For 10,000 it took 0.08 second. Selection sort is taking 6 seconds. Now you can see the actual difference, right? So 0.08 and this is taking 6 seconds. Perfect. Now we can run it for 100,000. I'm fine waiting for merge sort to return, right? Because merge sort took 0.8 second. Again, amazingly fast. 100,000 elements. 100,000 elements and took less than a second. What about selection sort? Selection sort is going to take a lot of time and I don't think we would want to wait for that much time. So my estimate is it's going to take somewhere around 5 minutes. It's going to take somewhere around 5 minutes. And that's because I kind of know that it will almost increase 100 times. It might increase 70 times, 80 times, 120 times, but somewhere around 100 times. So from 6 seconds, if it goes to 600 seconds, 600 seconds, that would mean 10 minutes, not 5 minutes, 10 minutes, right? So it will take a lot of time. We can't wait for that to happen, but it gives us a good idea that definitely merge sort is much better than selection sort. You should not, while you're doing experimental analysis, don't look at small numbers. Focus on large numbers. Obviously, some algorithms, they might be really slow for n is equals to 100. So in that case, we need to focus on those numbers. But at least in case of sorting, we saw that till 1000, it's hard to say which one is better. But after 1000, things became very clear, right? 10,000, 100,000, absolutely clear that merge sort is better. And in case of selection sort, if you keep doing this for larger numbers, you will see that if I increase n by 10, my time taken does not increase by 10, it increases much higher rate. It increases at a much higher rate. So seems like this function that we were looking for in case of selection sort, it's not going to be linearly dependent upon n, right? It will not be linearly dependent upon n. Because if it was linearly dependent upon n, then increasing n by 10 times should increase my time also by 10 times, right? So basically, that's what we are able to do using experimental analysis. Now we could basically look at a lot more values of n and try to find the exact graph and try to find the exact function. But it's going to be a little hard because of a couple of problems that we have already seen. First of all, it's not very reliable. For different run, it gives you different output, first of all, right? And secondly, it can be very cumbersome to, like if I think of 10 different algorithms, it might become really cumbersome to code all 10 to do the analysis, right? So in practice, we will not do the experimental analysis much. In the next session, we'll start looking at theoretical analysis, which basically means do not write code for it. You know the algorithm, find the time complexity, and when you know that which algorithm is best, only then you will code just that algorithm, not all of them. Okay, so that's something that we will do starting from the next session, and I hope you are able to understand what exactly we are doing in experimental analysis, and please implement this. Like just try to play around with the experimental analysis, try to plot a graph or two if you can, and try to see it for multiple values of n and see if you are able to make some sense out of it. Okay, thank you. Hi. So now let's talk about the theoretical analysis for figuring out the time and space complexity for algorithms, right? So what do we mean by theoretical analysis? The idea is that I don't want to write code for all the algorithms that I have to figure out which one is best. That sounds very, very stupid. Why should I have to write so much code just to figure out which one is better? So instead of doing that, we will be doing a lot of math, we'll be doing a lot of calculation to figure out which one is actually the best algorithm, and we'll try to do the quantification as well. Like we'll quantify how fast or slow each algorithm is. Okay. So why I don't want to do experimental analysis? First of all, we'll have to implement all of it. Second, we'll have to control the environment very tightly in case of experimental analysis to do the analysis properly. Because if you have multiple processes running on your system, that means every run can take different amount of time. So that's going to affect. Third problem is that you will have to design your test cases very carefully. So one test case might be really bad for one algorithm, but it might be really good for some other algorithm. So you need to pick test cases which are neutral to these algorithms, right? So for example, if I give a sorted array to selection sort, it's going to take a lot of time. But for insertion sort, a sorted array works really, really fast, right? If I give a sorted array to insertion sort, it just it sorts the array which doesn't have to do much, but it basically doesn't do a lot of work in case of a sorted array. Selection sort, whereas, will have to do all the work even in case of a sorted array. So if I use a sorted array as my test case while comparing insertion sort and selection sort, I might say that insertion sort is way faster. It might even be faster than merge sort or quick sort, but that's not going to be the case when you take any other input, right? So because of all these reasons, we don't tend to do experimental analysis, we tend to do theoretical analysis. Okay, so how do we do theoretical analysis? So given an algorithm, what we are going to do is, we are going to, let's say this is the pseudo code for the algorithm. We don't have to write the pseudo code, we just know what is the process. So given the algorithm, what we want to do is, we want to see how many operations this algorithm is going to do for input size n. See, while you're doing theoretical analysis, there is no way you can say it's going to take 2 seconds. You can't be so precise. It depends upon which computer it's going to run on. It depends upon a lot of those things. So we can't say exact how much time it's going to take. So instead we're going to talk about the number of operations this algorithm has to do, right? So if one algorithm has to do, let's say 10 to the power 5 operations for some particular n, whereas the other algorithm has to do 10 to the power 10 operations for input size n, then obviously we know this is much faster because it has to do less number of operations. And what do I mean by operation? Operation is basically any work like plus, minus, multiplication, divide. If you're doing if, you're checking if condition, there is an equal. All these are very small operations and we consider them as unit operation. Whereas if you have a for loop which is running n times, and whatever you do, so basically this is not a single operation. You are doing this n times, right? You are repeating this work multiple times. So this is not a single operations. All these are single operations which basically we will use as unit operations while we are counting the number of operations our algorithm is taking. So we want to find out how many operations our algorithm requires for an input size n. And that's how we are going to figure out which algorithm is better if we have multiple algorithms, or we will figure out how much time a particular algorithm requires. So even if we have just one algorithm, we want to figure out how much time it's going to take. And we are using operations as a proxy for time because we realize that finding exact time is not going to be possible for us. So let's focus on operations, which is a very good proxy for time. More number of operations you require, more time you are going to need, right? So works pretty well. Perfect. So let's do one thing. Let's find the number of operations for finding factorial. This is the iterative factorial, right? So how does iterative factorial look like? It looks something like this. For I going from 1 to n, we do answer is equals to answer into I, and then we can return answer, right? So we start with answer is equals to 1, we take an I which goes from 1 to n, and we keep multiplying this I into answer, and we eventually return our answer. So how many operations will this require? Now this assignment is one operation. Returning, we can say, is another operation, right? There are two operations plus. This multiplication is again one operation, but this multiplication is not happening one time. It's happening repeatedly. How many times? This loop is running n times, and every time this loop runs, this is executed. Is this the only line? So in a way I could have said n times I am doing one operation, this operation. But that's not really true, because when you're running this for loop, this I value will be incremented for you as well, right? I will increase, I will start from 1, it will increase as well. So whether you are writing that increment here by writing I is equals to I plus 1 in some of the languages, or whether you are just using something which auto increments I, doesn't matter, the work is getting done, right? So you need to account for that as well. So I could say it's 2n plus 2. So this is the number of operations my algorithm requires for input size n. And as expected, it depends upon n. If you ask for a factorial of a large number, my algorithm is going to take more time. If you ask for a smaller number's factorial, it's going to take less time. And seems like it's linearly dependent. If you increase n by 10 times, my operations will also increase almost by 10 times, not by 100 times, right? So linearly it's growing. Generally, what we will do, we will not worry about the exact count. What we will say, hey, there is some k work which is happening here and here. Instead of counting exact number of operations, 1, 2, 3, let's say some constant k number of operations, or let's say k1 operations. And then you are doing some work n times. How much work? Let's not worry about whether it is 2, 3, 4 work. Let's say some k2 work is repeated n times. The exact numbers are not going to be that important for us. What's going to be more important is what is this function's structure. Is it looking something like this, or is it looking something like this? This is going to be more important. The structure is going to be more important than these exact values. They are important, they are going to make a difference, but in our analysis we will just focus on, okay, so seems like there is some constant work that is getting done, that is k1, and then we have a for loop here which means some work is repeated n times. So we have k2 into n. That's how we will be doing our analysis. So finding the number of operations is like 90% of the work done. If you are able to get to a structure like this, 90% of your work is done, and in the next session we will see what is that remaining 10%, and then eventually we will do this whole analysis on a bunch of algorithms. Okay, perfect. So please take couple of problems and see how many operations it requires. It should not be that hard, and you should be able to get to the answer for those couple of algorithms. Just try for a couple of them, and then we will try more as we are going through this lecture. Thank you. Hi. So in this session we want to talk about a notation which you will hear almost always till the time you are working in computer science. Right? If you are writing software or you are giving interviews or you are taking interviews, this is a notation that you will hear so many times. It's called big O notation. Okay. So generally when two people are discussing, hey, my algorithm is very fast. So the second question will be, how much time does it take? So in the last session we saw that we might say, hey, it takes k1 plus k2 n operations, right? That is one way to quantify how much time or how fast your algorithm is. Or I could have said, hey, it takes k1 plus k2 n plus k3 n square. Or some other algorithm might be taking k1 plus k3 n square, there might not be a n term. And there might be, let's say, a k4 log n component as well. So what I'm trying to say is the structure can be very complicated. But we don't want to talk about this complicated structure. We want to talk about, like, we want it to be very simple. Just one thing that you say which tells me enough about a uh, particular algorithm. Okay. So we can go through the formal definition of big O and I'll explain you all of that. But the basic funda is, let's say I have an equation like this. Now if you look at this, we are not going to be worried about small values of n. So n, as n increases in size and keeps increasing, it becomes larger and larger. What do you think is the most important term here? What would be the most important term here? So So if you will see, as n increases, this doesn't increase at all, right? It stays k1. This increases at a very slow pace. Log n increases very slowly as n increases in size, right? N increases decently fast. It grows as fast as n. But if you look at n square, it grows rapidly fast as n increases in size. As n keeps increasing, going to larger numbers, n square increases rapidly fast, right? Extremely fast. So as n goes to larger and larger numbers, out of these four terms, one term that's going to dominate all of it is going to be k3n square, right? It's going to be k3n square. So while we are communicating with somebody, we don't tell them the exact structure. We just tell them the largest term. We just tell them the highest degree of n, the term which contains the highest degree of n. That's where we are going to focus on. That's what we are going to talk about. So if I am telling somebody, hey, my algorithm A is very fast, it's n squared, then they would understand that there is some constant which should be multiplied to n square, and this is the amount of time your algorithm is taking. Even if there are some additional factors which are basically smaller in degree compared to n square, we are not going to be worried about them, because as n increases in size, this is going to dominate the rest of these terms. So we just focus on the largest degree of n, the term which has largest degree of n. For example, let's pick one more example. Let's say k1 plus k2 n square plus k3 n cube plus k4 n square log n. Out of these terms, what would be your algorithm? Like, how will you quantify your algorithm in one term? This you can ignore. You can ignore this with respect to n cube. N cube is huge compared to n square, grows much faster than n square. So here we can get rid of this as well. N square log n. This is larger than n square, right? This is larger than n square, but this is going to grow slower than n cube, so we can ignore this term as well, and we can say our algorithm is n cube algorithm, right? It's n cube algorithm. Perfect. So now let's talk about the big O notation in a little more detail with proper definition, so that we understand how we are able to, how do we say some algorithm is big O of something. What exactly is this big O notation? So an algorithm A is called big O of n square, let's say, for example, if time taken by algorithm A for input size n is less than equals to some constant k into n square. I have taken an example of n square. This could be anything else. So let me repeat this. Don't get confused by this. An algorithm A is called big O of n square if some constant k multiplied with this n square is an upper bound on the time taken by algorithm. Right? It has to be an upper bound. Basically what we're trying to say is it cannot get worse than this. This is the maximum my algorithm is going to take time. It's not going to get worse than this. Right? So that's how we define the big O notation. If somebody is telling you, hey, my algorithm is big O of n cube, this basically means they are trying to tell you when they found out the operations that their algorithm B requires, the most dominant term in that equation, in that structure, was some k into n cube. That was the most dominant term in that formula that they were able to get to. Right? That's what they are trying to tell you. That's how we define the big O notation. Technically speaking, if an algorithm A is big O of n square, that means time taken by algorithm A for an input size n is less than equal to some constant k into n square. if you see, technically speaking, I could say this as well. If it's less than kn square, it has to be less than kn cube. So in a way, kn cube is also an upper bound on the time taken by algorithm. So I can say my algorithm is big O of n cube. What did we mean by big O? We meant that k multiplied with that whatever you have written inside here should be upper bound on the time taken, and it is an upper bound on time taken. So technically you are correct. Your algorithm is big O of n cube, but in practice, whenever somebody is asking you what is the time complexity of an algorithm, you are supposed to find the tight bound. Upper bound does not mean that you give a huge bound, you need to give a tight bound. If you are saying n square, then I am assuming it's not n, right? It means n cannot be an upper bound, n square is the upper bound. If you say n cube, then I am assuming your algorithm is slower than n square and it works in n cube. So you need to give a tight bound. Technically it is correct that my algorithm is big O of n cube by definition, but in reality I am going to assume that you don't understand time complexity well if you tell me an algorithm is n cube whereas it was actually n square. Okay, so that's the big O notation. Now let's just quickly see, in case of factorial, we were able to get to the operations required for factorial were, we said it is k1 plus k2n, right? So in a way what I can say is, to make you a little more comfortable with getting rid of these terms, I can say number of operations are less than equal to k1n plus k2n, right? A dramatic, very high-handed approach to basically instead of k1 I made it k1n, and I am saying it is less than whatever the number of operations are required, and I think like the number of operations are less than this. If they are equal to this, then I have increased this number by a lot, and I am saying it is less than equal to k1n plus k2n, which I can say is k1 plus k2 into n, so some constant into n. What I am saying is the time taken is definitely less than equal to k1 plus k2n, and I can call this as k. So I have proved for factorial the time requirement or the number of operations required is less than equal to some constant k into n. That means factorial is big O of n. Factorial is big O of n, right? Similarly, let's pick another example. Let's take an array. Let's find the largest in the array. How do you find the largest element in the array? Now I'm not even going to write that pseudocode kind of thing for now, right? How do you find the largest? You make an L, you take an L and you, let's say, put A0 in it, and then you go to the next element and check. If the next element is greater than L, you update L. Then you go to the next one. If the next element is greater than L, then you update L. Then you go to the next one. If the next element is greater than L, then you update L. So how much work are we doing here? So we are initializing few things, we will be returning something in the end. So some constant k work for sure, right? For initializing some stuff and eventually returning something. And then we are going to each element one time, each element only once. The first element we went, we checked. Second element we went, we checked. Third element we went and we checked. So n times we are doing some work. How much work? At each element you are comparing with L and you are updating L. Might or might not, but whatever it is, it's some constant, right? One comparison, one if, then one updation. Even in the worst case, like all these combined, you will take this much time. So some constant into n. So very similar equation, and we will again say this algorithm is big O of n. with the same logic that we used in case of factorial. While we are doing all of this analysis, we need to look at the worst cases, right? Don't assume, for example, if you are looking for linear search time complexity, there is an option that I'll find my element at the 0th location itself, and I don't have to go through the rest of the array. My linear search algorithm can be super fast if I find the algorithm, if I find the element at the first index itself. It will not have to go to the rest of the elements. But that's not something that we are going to think about. We are going to look at the worst cases. What is the worst input that you can give me? And for that input, how much time my algorithm is going to take? That's what I am going to look at while finding time complexities. Almost always, right? Like there'll be a couple of cases where we'll not look at the worst cases, and we'll talk about that. But almost always, and for now, just think that always we'll be looking at the worst cases to figure out the time complexity and space complexity of our algorithms. Okay, great. So we have looked at a couple of algorithms which were taking linear time. Why linear? Because it is growing as fast as n. In the next session we'll look at some like few algorithms which are a little more interesting, which are taking non-linear time. They grow non-linearly with n. Okay, perfect. Thank you. Hi. Now let's make things a little more interesting, right? So now let's look at recursion. So we have already seen how factorial, the time complexity of factorial, what it looks like in case of iterative solution. But we have also solved factorial recursively. So let's see if the time complexity changes or it stays the same. Okay. So the way we had written our factorial code was this. We were returning 1, otherwise we were saying return n into factorial of n minus 1, right? Now if you see, this code is very simple. There is no for loop, there is no while loop, there is nothing happening here. We are just doing some constant work and we are making another function call. So you might be tempted to say this is constant, like it's not going to do, like irrespective of n, it's going to be very fast. But that cannot be the case, right? I cannot find factorial n without like which is independent of n. Like it has to depend upon n, the amount of time I'll require. And that's true here as well. So basically what's happening is, to find n you are saying here I need n minus 1. To find n minus 1 you are saying I need n minus 2. So it keeps going till it reaches 0. Now how do I find time complexity for problems like these? In case of recursion, it will actually make sense to write recurrence relation. What does that mean? That basically means the time taken by this algorithm for input size n will be equal to some constant work. What is this constant work? I am checking something, then I am doing this multiplication as well. Some constant work plus t of n minus 1. What it is saying is, I need to find time taken by this algorithm for n minus 1. Whatever time that takes, that function call takes, other than that I am doing only constant work. I am doing one multiplication and I am doing this if check. That's the recurrence relation that we can write. What is factorial saying? To calculate factorial of n, I am going to take the same amount of time as what n minus 1 take, plus I need to do some k additional work. So once you reach this recurrence relation, things will become very simple for you to find time complexity of recursive solutions. So you have this. Now to solve it, we can say Tn minus 1 is equal to Tn minus 2 plus k. Tn minus 2 is equal to Tn minus 3 plus k. Now if you add all these equations, these will cancel out. Everything will cancel out. Tn will become k into, how many equations do I need to add? The last equation will be T1 is equals to T0 plus k. This will be my last equation. So I have n equations. This started from n to 1. So n equations. So k into n plus T0, which is a constant. T of 0, it comes, it checks the if condition and returns. So some constant work. So this is k2. So the amount of time recursive factorial takes is k1 into n plus k2, and we can ignore k2. That means the time taken is k1 into n. That means factorial, even when it is recursive, is taking big O of n time. How did we come here? How did we reach here? We were able to reach here by first writing this recurrence relation. Okay, so it's very important you write the recurrence relation correctly. The second step will be to solve this recurrence relation to find out Tn. Okay, perfect. Thank you. Hi. Now let's look at another algorithm which is very fun, right? It's called binary search. So binary search we have seen, you might have solved using iteratively or recursively. You might have done it both ways. But the concept is actually very similar. How do you do it when you're doing it iteratively? You say, hey, go to the middle element. Depending upon whether the middle element is larger than the search element, you either look at the right part or the left part. And recursion works exactly the same way, right? So to find time complexity, they will work exactly the same way as well. Okay, it will work exactly the same way. So let's try to write the recurrence relation for binary search. So what do I need to do? To find an element in an array of size n, first of all, I need to calculate the middle, some constant work. I need to compare this search element with middle, some more constant work. And then, depending upon whether what is the result of comparison, I will have to update my boundaries to be either this part or this part. So some more constant work, right? I have found the middle, constant work, compared with the search element, constant work, and then updated the boundary to be this part or this part, again some constant work. So I'm doing a lot of constant work, plus now that you have done this much work, your problem has reduced from a problem of size n to a problem of size n by 2. So Tn is k1, some constant work, plus same problem but half size. So Tn is equals to k1 plus Tn by 2. Your problem is now half sized. That's the recurrence relation in case of binary search. Okay, so now let's solve this recurrence relation. Some constant k. Okay, so let's write it one more time. Tn by 2 is equals to Tn by 4 plus k. This means Tn by 4 is equals to Tn by 8 plus k. And we will keep going like this for just one element. If I have only one element, what do I need to do? I need to compare S with that particular element to get to my answer. So again, some constant k. Now, if you add all of these will cancel out. So whatever will be left is something like this. K into x. And what is x? X is the number of terms after which you reached T1. Okay. See, it's not going from n to n minus 1 to n minus 2 to n minus 3. If that was the case, I will have n equations here. But the way it is going now is from n we go to n by 2. From there we go to n by 4. From there we go to n by 8 and so on. So it's not n. We don't have n equations here. We have lesser equations here. So how many equations do we have? So after one equation it became n by 2. After next equation it became n by 4, which is n by 2 square. Then it became n by 2 cube, that is n by 8. Then eventually it became 1. So after 3 equations it was n by 2 to the power 3. So if you are actually taking x times to reach to 1, that basically means n by 2 to the power x is equal to 1. Right? That's what it has to be. First time you divide by 2, then you divide by 2 square, then you divide by 2 cube, then you divide by 2 4 to the power 4. So eventually it's becoming 1. So if after x equations I am reaching 1, this is the equation that has to be true. Right? This basically means n is equals to 2 to the power x. This basically means x is equals to log of n. Okay? What this means is, if you reduce by half every time, right, it becomes much faster than linear. That makes sense, right? For example, if I start from 1024, I will reach 512, then I'll reach 256, then I'll reach 128, 64, 32, 16, 8, 4, 2 and 1. So from 1024 I was able to reach 1 in how many terms? In how many times? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just 10 divisions. 10 times I had to do this work and I have reached from 1024 to 1. So if I start with an array of 1024 size, within 10 calls I will reach a single element. So it's much faster than n. N would have meant I will take 1024 times. But binary search is much faster. Dividing by 2 is like reduces the number very quickly. Okay. So basically what we are saying is, first time whenever it was n, next time it became n by 2, then it became n by 2 square, and the last time it is n by 2 to the power 10, because we have done it 10 times, which is equal to 1. That means n is equals to 1024. Right? So using this equation we can say x is equals to log n. So we'll take log n times to reach 1. That means binary search is k into log n. This is a constant. We can say binary search is big O of log n. Extremely fast. Extremely fast. Compared to linear search takes n time. It's big O of n. Binary search is big O of log n. It's super fast. Obviously it requires the array to be sorted. That's a problem in itself, right? But binary search in itself is an amazing algorithm with time complexity as big O of log n. Okay. Now please try to find time complexity for a couple of recursive algorithms, and it will give you the right ideas around how to solve recurrence relations and how to make recurrence relations. These are two very interesting ways, like two very interesting parts of finding time complexity of a recursive algorithms. Not all recursive algorithms, you will not be able to find time complexity of all the recursive algorithms using this methodology. You can make the recurrence relation for a recursive function, but sometimes solving that recurrence relation can be hard, and we will look at some other ways for that as well. Okay, but in general, if you have a recursive algorithm, the first step will be find recurrence relation, that is this equation Tn is equals to T of something plus some constant or plus some other work, whatever you are doing. The second part will be solve the recurrence relation. I think this is generally something that you will always be able to do in case of recursive algorithms. Once you have done this, your work will be to solve it as well. Okay, perfect. So please practice with some recursive solutions and will give you a lot more confidence on how to find time complexity of recursive functions. Thank you. Hi. So in this session I will talk about the time complexity for merge sort, right? So merge sort, let's first quickly brief through what the algorithm was, right? So in case of merge sort, what we had to do, given an array, what we decided is, let's split it into two parts. We called merge sort on individually both of them. So let's keep writing the work, right? So first of all, splitting. So if you have to copy the elements, and even if you use whatever way you try to do, like for example in case of Python you can do slicing. So if you are copying one by one or you are slicing, in both the cases new arrays are formed, the elements are copied. So to copy n elements into two arrays, you are doing some constant k1 into n work. This is not for free, you can't just split for free, you are copying n elements, that will take k1 into n work. Then you are calling merge sort on both of them. So the total time is tn. To me it looks like this is 2tn by 2. Tn by 2 work for this, tn by 2 work for this. So you have to do twice of tn by 2 work. This is the amount of work you will be doing. Now both of these are sorted. Both these are sorted. And you have to merge these two into the original list that you had or the original array that you had. How do we do that? So the algorithm for that was very simple. We started with an I and a j here. We compare whatever is smaller, whichever element is smaller, we copy that into the original array and move I. So what is the work you do? You're comparing two elements, and with this constant work you are able to decide one element of output, and then you increment I, again some constant work. So some constant work that includes comparison and increment, you are able to find one element of output, and then again you do the comparison and then copying and the increment, and you are able to get one more output element in the output array, right? So you have one more output element in the final array that you want. So to me it looks like this I has to cross all these elements, this j has to cross all the elements. So n by 2 work, n by 2 work, total again you are doing some k2 into n work. So for every element in the output array you are doing some constant work. How many elements do you want in the output array? These are n elements. So this is the amount of work you will be doing. Okay, so let's review this again. So first of all you are doing this much work. Then you are doing two calls to merge sort, that is 2tn by 2, and then you are merging these two sorted arrays into the original array and you are taking k2n work again. To me it looks like tn is equals to k1 plus k2n plus 2tn by 2. This is a constant k, k1 plus k2 can be another constant k. So the recurrence relation is going to be this. The recurrence relation is going to be this. It's very important that you get to the correct recurrence relation, otherwise you can't get to the correct output. So some people, they don't realize that we are calling, this is wrong, they don't realize that we are calling two arrays, two half-sized arrays, we are calling merge sort on them. So this is incorrect. right? If you use this, you will not get the correct output. Some people realize this, but then they don't realize that we are not doing constant work. We are splitting the array, then we are merging the arrays back. We are doing kn work. So this is wrong as well. So getting to the correct recurrence relation is very, very important. Now once you have that, now we need to solve it. How do we solve it? Let's try to use similar method that we have used earlier. So Tn by 2 is equals to 2Tn by 4 plus k. Instead of n, now will be n by 2. Tn by 4 is equals to 2Tn by 8 plus kn by 4 and so on. Then we already know T1 is equals to just a constant k. Okay, just the constant k. Now if I add these, this Tn by 2 and this 2Tn by 2 is not getting cancelled. So in order to cancel these, I need to multiply this by 2. Now as soon as I multiply this by 2, this will become 2Tn by 2, this will get cancelled. Well, this will become 4Tn by 4, right? So if I add the first two equation, this will become Tn is equals to, so this Kn plus this Kn by 2 multiplied by 2 is again Kn plus 4Tn by 4. So instead of you had 2Tn by 2, now you have 4Tn by 4. So the next equation you will have to multiply by 4 so that this 4Tn by 4 gets cancelled with this 4Tn by 4. But the interesting part is you had Kn in the original one, you had Kn by 2 in the next one, which got multiplied by 2 and you got Kn here instead of Kn by 2. And now you are multiplying by 4, this 4 will get cancelled and you will get another Kn here. And this will get cancelled. Instead, you will get 8Tn by 8. So 4 into 2Tn by 8 will become 8Tn by 8. And that's how you need to do all these additions. So let's write it again. So what you will have to do is, and so on. And I'm saying T1 is equals to K. So while you're adding, you will have to multiply this with 2, this with 4, this with 8, and so on. And from all these terms, these will get cancelled. This 2Tn by 4 becomes 4Tn by 4 and this becomes 4Tn by 4, they get cancelled. This 4 into 2, 8Tn by 8 gets cancelled with this 8Tn by 8. All of these get cancelled and what you get is Tn is equals to Kn from this part, then 2 multiplied by Kn by 2, Kn, plus Kn by 4 multiplied by 4, Kn, plus Kn by 8 multiplied by 8, Kn. So you keep getting these Kns till you reach T1. And when will you reach T1? How much time will you take? How many times you will have to write this recurrence relation to eventually reach T1? Let's assume x times. Let's assume x times. So how do you get this x? You had n, then it became n by 2, then it became n by 4, then it became n by 8, then it became n by 16, and so on. You eventually reached 1. So if you're taking x steps, so after one step n by 2, after 2 steps n by 2 square, after 3 steps n by 2 cube, after x steps you would have reached here. And this has to be equal to 1. This basically means x is equals to log n. You have these kn terms repeated log n times. So that means your time taken for input n will be kn into log n. This is the amount of time merge sort is going to take. The time complexity is big O of n log n. much better than selection sort, bubble sort and insertion sort, which will all n square algorithms. N log n is much faster than n squared, right? It's much faster than n squared. Okay, so that's how you find time complexity of merge sort. Okay, thank you. Hi. So in this session, I want to talk about a problem which is very interesting. We have already solved it. This is called Fibonacci. So we have seen the iterative as well as the recursive solutions. But in this particular session, we'll be talking about the recursive solution for Fibonacci. Okay. So what was the recursive solution like? So we said fib of n, if n is 0 or n is 1, return 1. Otherwise, we were returning fib of n minus 1 plus fib of n minus 2. Now, extremely simple code, right? If you look at it, t of n, you're just checking something. So, some constant k plus t of n minus 1, because you're calling on fib of n minus 1, plus t of n minus 2, right? The recurrence relation is as simple as this. So, let me write this down again. Tn minus 1 plus Tn minus 2 plus k. What this basically means is, what we are saying is, this function is making two calls, and then in itself this function is not doing much, it's doing some constant work, that's it. Now the problem with this recurrence relation is, if you try and solve this recurrence relation, it's going to be a little tricky, right? It's not as simple as factorial or merge sort. Like, it's going to be like pretty hard to solve this recurrence relation. So we're going to look at this solution, look at this problem from a little different angle. And that again is something that's going to work really well in a bunch of recursive solutions. So instead of looking at the recurrence relation, let's try to see how recursion calls are working. So you got input n. To find answer for input n, you're going to call for n minus 1 and n minus 2. What I'm actually trying to do here is, I kind of realize that each function call is doing some constant work, right? Each function itself is doing only constant work. So if I can somehow figure out how many function calls are happening, I'll be sorted, right? Things will become easy for me. So if I know how many function calls are there, then that will be my time complexity, because each function is doing constant work. So that's the only thing that we need to do, right? So if we know how many function calls are there, we will be able to solve this problem. Perfect. So what I'm saying is, a function which got input n is calling a function n minus 1 and n minus 2. N minus 1 is calling n minus 2 and n minus 3. N minus 2 is calling n minus 3 and n minus 4. Wow. N minus 2 is going to call n minus 3 and n minus 4. N minus 3 is calling n minus 4 and n minus 5. N minus 3 is calling n minus 4 and n minus 5. N minus 4 is calling n minus 5 and n minus 6, and so on. You will keep going down those links. You will keep going down like this, right? Like this is going to get repeated on and on. So initially you made only one function call. That one function called two functions. These two functions are going to call four functions. These four functions are going to call 8 functions. These 8 functions are going to call 16 functions, and so on. And so on. Seems like we are calling huge number of functions. In case of factorial, n was only calling n minus 1. right? Then n minus 2, then n minus 3. So you reached till 1, so you had n function calls. That's it. Here seems like we're doing a lot more function calls. How many function calls? So if you look at it, here you have n, here you have n minus 1, here you have n minus 2, here you have n minus 3. So the height of this whole thing will be n. N minus 1, n minus 2, n minus 3. Eventually this will finally come down to 1. So this thing will have n levels. Each level, but here if you look at it, n minus 2, n minus 4, n minus 6, n minus 8, from this side it looks like it will be n by 2 levels, right? Because you are reducing by 2. So after n by 2 you will reach 1. So you will not go below that. So in the worst case we can assume this has n levels, and if it actually has n levels, the first level has one function call, second level has two function calls, the third level has 4 function calls, next level has 8 function calls, next level will have 16, next level will have 32, and the last level will have 2 to the power n minus 1 function calls. This means you will have, so sum of these terms is 2 to the power n minus 1. Seems like you will have exponential number of function calls. Each function is doing constant work, so you're doing this much work. So the time complexity of Fibonacci factorial is big O of 2 to the power n. 2 to the power n is horrible. It's much worse than n square, it's worse than n cube, it's horrible. Just to make you realize how bad 2 to the power n is, 2 to the power 100 is a huge number, and finding 100th Fibonacci number is not going to be possible from our code, right? 2 to the power 100 itself is going to be a pretty big number, right? So 2 to the power 10 is 1024, so this is 10 to the power 3, and then basically you are saying, so 2 to the power 100 will basically be 10 to the power 30. So this huge number is basically, these are the number of operations that you would need to do to find 100th Fibonacci number. In general, we assume that 1 second, in a computer in 1 second can do 10 to the power 8 operations, right? To do 10 to the power 30 operations, you would need 10 to the power 22 seconds. So we will not be able to do it. This is again like something that we'll not be able to do. So any algorithm that you have which take exponential time is pretty much useless, because it's not going to work for numbers. Like even after 40, 45, it'll become really slow, and we'll not be able to use that algorithm. Okay, so that's how we found for Fibonacci the time complexity. How did we do it? We saw each function, and we saw that each function takes k time, even if it was taking kn time. So whatever time, we'd figured out that okay, each function is doing this much work. Let's figure out how many function calls are there, and that will tell us the time complexity of the overall function. Okay, that's how we did it. To find the number of function calls, we created this structure just to visualize it, that what exactly is going on, what is n calling, what are these functions calling next, and so on. We generally call it the recursion tree. We call it the recursion tree. So we drew the recursion tree to figure out, to understand the calls that recursion is doing, which helped us figure out that we are doing exponential calls, and if we are doing exponential calls, the time complexity is exponential. Makes us realize the Fibonacci recursive code is actually pretty bad. If you want, you can try to run it for n is equals to 50, 60, 100, and it's not going to work. Okay, thank you.